Hello and welcome to Empowered Learning. This video is the third video in the video series for variation of parameters. So in this video, we're going to go and do a deep dive into how and why does variation of parameters method work, okay? And so I'm going to pretty much read from the notes I've written out here just to kind of make this as efficient as possible, but I will stop in places to try to clarify. So what I'm trying to get across here is why we actually call this method variation of parameters in the first place, okay? And so to kind of give you a summary of what's going to happen here, we're going to make some assumptions. We're going to take some facts about what we know about homogeneous and non-homogeneous equations as far as what their solutions should look like and what we should expect for them to look like. We're going to make some assumptions and then say, based upon these assumptions, we need to find out what conditions our non-homogeneous equation would have to meet in order to satisfy those assumptions that we have come up with. And what we're going to see is that in doing that, and using the reduction of order process, we're going to come about an equation that's going to actually be a first order linear equation. It's just not going to look like it until we kind of finagle things to make it look that way. But once we get to that point, we're going to see that all of the unknowns that we have defined along the way, we're going to see that we're going to have one more unknown than we do equations to be able to represent everything. From that point, we will see that since I have basically one more unknown than I do equations, I can allow one of those unknowns to equal anything. And it's going to turn out that if we allow one of the unknowns that we have to actually equal 0, it makes everything easy to come down to the two equations that we're used to seeing in the systems of equations for the variation of parameters process, especially when we're talking about second order differential equations. So in a nutshell, that is what we're going to be doing here. I'm just going to show you the process from beginning to end so that you can have a feel for how this works. All right, so without loss of generality, we want to consider deriving the method of variation of parameters for a second order linear homogeneous ODE. Afterwards, we'll state the extension of this method for an nth order ODE, and hopefully you'll see the pattern that continues to happen. So we want to consider this second order linear non-homogeneous equation, okay? And we know that because we're assuming that our g here is going to be a function that's not equal to 0. Then it's going to follow that the solution of this ODE should be of this form. And again, if you're familiar with solving linear non-homogeneous equations by using method of undetermined coefficients, then you're already familiar with why I'm actually saying this, okay? So we know that y sub h is going to be the corresponding homogeneous solution to this equation, just basically this equation, but it equals 0 instead of g here. And yp is going to be our particular solution. So now that we know that this total solution of this equation should look like this, we want to observe a few facts about our situation. So the first fact I'm calling 1i is that our homogeneous solution here is going to be the sum of two basis functions multiplied times a constant for each of them, which is a fancy way of basically saying that the two functions y1 and y2 that are solutions to our homogeneous equation, any linear combination of these two will also be solutions as well. And we know that, of course, y1 and y2 create a basis for our homogeneous solution here. So because we're able to say this, that means that when G is equal to 0, these solutions here follow the principle of superposition, which again, just basically says that if I got two functions that are a basis for my solutions for my differential equation, then it means that any linear combination of those two functions will also be a solution. That's basically the outcome of superposition. Now, we know that star is a non-homogeneous ODE, meaning that we know that G is not going to be equal to 0. So we know that those solutions, whatever they are, can't follow the principle of superposition as we've stated here. Okay. And so without going into a whole lot of detail, one of the things that we know is that a homogeneous solution is really the difference in between two particular solutions. Okay. And so that's one of the things that should have been found out whenever you were studying how to solve these types of solutions here. Basically, whenever you learn how to first solve non-homogeneous linear ODEs, that's one of the things that should have been pointed out too. Okay? So if we can find two particular solutions to a non-homogeneous ODE, take the difference of them, what we end up having is a solution to the homogeneous equation. That's always true. Okay. So we know that whatever our solutions are going to be for our non-homogeneous solution, which we know looks like this, is not going to follow superposition in how we understand it for the homogeneous equations. Okay. So here, if we let y sub a and y sub b be two particular solutions, then again, the difference of these two solutions should be homogeneous solutions. So I've already stated that. Fourth thing is that if we let y sub w and y sub z be two known or assumed solutions to an ODE, regardless of the type of ODE, and what I mean by that is regardless of whether it's going to be a second order linear with all constant coefficients, or if it's going to be an Euler-Cauchy or something else. Okay. Whatever it is, we know that if I have a known solution to a differential equation, I can always find another one by using the reduction of order method. Okay. And I'm just going to call it the rule method for short here. Now, the thing is that in us employing reduction of order, there's going to be certain things that we expect. Okay. The first thing is that if I know that if I have a known solution, or in the case of what we're going to do here, a assumed solution, if I assume that this is a solution, then this should be another known solution. And if I assume that this is a solution to my non-homogeneous ODE, then this should be one. And that comes directly from what we know about reduction of order. Okay. So if we assume that these two can be solutions, then u times y sub w and v times y sub z should also be solutions as well, where the u and v should be functions of x. Or let's say if you are doing it in your independent variables of t, then it'll be functions of t. Now, we can conclude from our observations that, first off, our particular solution is going to be a solution of star. If that's the case, then y of p will not be able to be expressed in this form, meaning it won't be able to be expressed like how we did the homogeneous solutions here. Because remember, our homogeneous solutions could all be expressed this way as linear combinations of the basis function. Well, we're not going to be able to do the particular solutions that way. Okay. And again, that's because our y of p will fail to follow the principle of superposition. Number two, if we assume that two solutions to our original equation star are going to be these two that I mentioned earlier, then we could use reduction of order to state that these two functions are solutions to it, as I stated. And we know that since u and v are going to be functions of x, we may have to satisfy some conditions to force these two solutions and these two to all kind of work in our grand scheme of trying to find solutions for the non-homogeneous ODE. So in other words, I'm just saying if we force some things to happen through the process of working everything out, we may have some specific conditions that we need to satisfy. Okay. Now, from these conclusions, we know that our YFP is not going to be able to be expressed this way and be a solution. But, and here's where the derivation process starts. But what if we let K1 and K2 be functions of X instead of constants? Okay. If we did that, meaning that we let this be a function and let that be a function, and assume that our particular solution to our non-homogeneous ODE star could be written like this. So if we did, then YP would take on this form here. Okay. And so I'm just basically saying, instead of labeling it K1 of X and K2 of X, we're just going to call it U and V, like how we did over here. Okay. Now, if that's the case, since U and V are constants, we don't know, or are not constants. That's what this should say. So as U and V are not constants, we don't know if the principle of superposition would or would not apply here. Okay. So in other words, if we force these conditions on this, we don't know if any linear combination of results of U and V based upon what Y1 and Y2 are would actually work. We don't know that. Okay. So since it's uncertain if the solutions for our original ODE, non-homogeneous ODE, in this form would satisfy superposition, let's assume that it would. Okay. And if we made this assumption, then what other assumptions or conditions would have to be satisfied in order to make this situation work? So in other words, I'm saying, hey, I'm going to come up with another way of thinking about superposition, but it's going to be superposition in terms of linear combinations of known functions with other functions. Okay. So, and that's why I called it in the part 1 video a pseudo superposition. So we're going to say that, hey, we can have multiple solutions that are going to act like this. If I say all that is true, then in the process, what other conditions am I going to have to satisfy, and what other assumptions am I going to have to make in order to make that work? Because what we're going to find out is that, hey, this could possibly work, but I'm put inside of a box. I just can't do it and say this works for all things. Okay. I got certain conditions that I have to meet. So in performing reduction of order under these conditions, we'll answer the questions that I've asked up here, and we'll actually end up seeing what variation of parameters method looks like. So therefore, we're going to let our particular solution be of this form, and we're going to apply reduction of order. So we'll need to attempt to try to find U and V, okay? Because that's what we need. Because if we can find U, we can find V, and we'll already know what Y sub 1 and Y sub 2 is, because those two functions come from our basis of solutions from the homogeneous solutions, okay? Well, homogeneous equation, right? And so, well, we observe the following expectations as we go through the reduction of order process, okay? Now, we're going to apply reduction of order, but to do this derivation in a judicious and efficient way, you have to kind of know what it is that you're expecting from reduction of order, so that you can write out everything in a nice way that keeps you from having to do too much computation, okay? So here's the first thing. We know that in reduction of order, we got to find Y sub P prime and Y sub P double prime once we state that, hey, let Y sub P look like this. And we're going to have to take our Y sub P along with Y sub P prime and double prime, put it back into our equation, okay? Now, with reduction of order, we also are assuming that our other solutions based upon what we said here, y1 and y2. We're assuming that y1 and y2 are going to be solutions of our original equation, even though technically there aren't. We're just assuming that. So if that's the case, then we know that these two functions will also be assumed solutions of this equation here via reduction of order. Now, in the reduction of order process, one of the things that we expect to happen is that once we do all this substituting of y sub p prime, y sub p double prime, and we kind of get everything worked out, the terms that have the lowest order of u and v, mainly terms that have u in it and v in it, they're all going to add up. Okay, they're going to all add up and end up canceling to 0. Okay, so all terms with u in it, if we add it up, it should be 0. All terms with v in it, they should all add up to be 0. Now, the thing that you're going to see in this process is that what add up to be 0 looks like is going to be different than what you're traditionally used to seeing. Okay, and the next bullet point kind of gives a hint as to what that's going to look like. So we want to note that since y1 and y2 are actually homogeneous solutions of our corresponding non-homogeneous differential equation, this means that if I plug in y sub 1 into the corresponding homogeneous solution, or y sub 2, and I'm just using that since I have these two here, then that means that that result ends up being 0. And so we're going to see when we go through this process that the sum of all my terms in terms of u and in terms of v, they're going to add up to look something like this. Okay, and once I see a group of terms that looks like this together with either y1 or y2, I know that all those together will just collapse to be 0. Okay. Now, once all terms of u and v are canceled to 0, and since we are assuming that our force function g is not going to be 0, meaning that we're assuming that our equation is going to be non-homogeneous, the next thing that we are expecting is that our resulting equation, after doing all this substitution here, will be a first order linear ODE, since it is a second order linear ODE that we're starting off with. So remember, the whole point of reduction of order is to assume that we have solutions, take the derivatives as necessary, dump it into our ODE, and then eventually be able to rewrite our equation as an equation of one order or one derivative lower than what we started with. Okay, and so whenever our g is equal to 0, we know that this situation here ends up being a separable equation. Okay, meaning that we can arrange all terms in terms of x and all terms in terms of y on one side. Whenever it is not equal to 0, then that's when it becomes a first order linear. And again, we're talking about the case where we're solving second order non-homogeneous linear ODEs. Okay, so before we get into this, I want to recap and say we're assuming that y sub p is going to be a solution of this form, where u y sub 1, v y sub 2 are going to be solutions. And so because of that, we know that some of the things that we're going to expect is we're going to have to take the first and second derivative, plug into the ODE. We know that once we do this step here, all terms with u and v are going to cancel to 0, and that's going to help us in reducing the order of the equation. We note that anytime we see any collection of terms that look like this, we know that that's going to equal 0 if, of course, we find it with y sub 1 or y sub 2 in it. And then after we work all that out, the resulting equation has to be a first order linear ODE. It has to be. So if we don't get that, or if it doesn't look like that, we need to force it to look like that, okay? Because it should end up being that way. All right, so now we're going to go ahead and start the process here. So the first thing that we'll do is we'll assume that my particular solution is of this form. So I'm going to take the first derivative and the second derivative of it, okay? Now note, when I take this first derivative here, these terms have a u and a v in it. So I know that these terms here are going to eventually add up with something else to end up being 0, okay? So I take note of that, okay? When I take the second derivative, which is the derivative of the derivative, notice that if I take the derivative of this term here, I am not going to get any terms that have a u or a v in it explicitly, okay? So because of that, I'm going to judiciously leave this as just u prime times y1 plus v prime times y2, just a derivative of that. Now, if you remember, if you watch the part 1 and part 2 videos, you'll know that our end result here ends up looking like this. And I'm just going to go ahead and write it out so that you can kind of make this connection here. So this is what the end result ends up looking like. And notice that this term here is the same exact term that I have on the left side of this equation, okay? And also notice that it ends up equaling 0, okay? And we're going to show you later on why that actually is, okay? So this is another reason why we want to keep this particular term looking the way that it does, because it's going to help us out tremendously to keep it this way, okay? All right, so we have our y sub p, first and second derivative. So now what we're going to do is substitute everything in, okay? So all this that we see here is just yp double prime. All this that we see here is yp prime, and this here is yp. So I just threw it in. So from here, what I've done is I've taken the time to kind of group everything. And so just basically multiply the A's on through the all terms here, B's here to all terms, and C here, okay? So the next step is I want all terms that have U and all terms that have V put together, okay? Now, the first thing I notice is that I have this term and I have this term that will not produce any terms that have U and or V explicitly shown. So I'll go ahead and list those two first, okay? The next thing I notice is that I have this term here and I have this term here. These two terms also do not have U or V's explicitly shown. So I go ahead and list those. The remaining terms that I have, if you see, if I circle all of them, all these terms have either U or V explicitly shown. And so here I go ahead and group them in these two terms here. And notice that what we have whenever we add all these terms up with U and V, it looks exactly like the thing that we said earlier about our homogeneous solution outcomes, okay? So this looks exactly like our homogeneous equation here, where k could be either 1 or 2. So when k is 1, we have this, ends up equaling 0. When k is 2, ends up having this, ends up equaling 0. So all terms with U and V, which is the lowest order terms here, because notice that we have U prime, we could have U double prime, we got V prime, we could have V double prime. So we could have all those things. Of course, we don't have it, but my point here is that in an equation like this, the lowest order that we could possibly have for u and v is just going to be u and v itself. Okay. And we know those terms have to go to 0. And so we see that that happens. So now we know that our equation here is just going to reduce to all these terms here on the top row. So we just have all of this. Okay. Now at this point, we know that whatever this is, this has to be a first order linear ODE. It has to be. It doesn't necessarily look like it right now, but it has to be that. Okay. And so note, since we canceled out all like terms of u and v, which means that, of course, by what I was saying up here, that has to equal 0, we now can concentrate on making this equation here look like a first order linear one. Since the expression u prime y1 plus v prime y2 shows up, and this should, and again, just to make sure that you're not confused with this, I have that in quotation. So this is u prime y1 plus v prime y2. Since that expression shows up in the second term here, and the derivative of this shows up in the first term here, then, and also we know that this particular expression here can be assumed to be some function of x. Okay, we know that because y1 is a function of x. We know that y2 is a function of x. And we know that since u is a function of x and v is a function of x, then u prime and v prime have the possibility of being a function of x as well. So we're just going to assume that. Okay. So for simplicity, we're just going to let this expression here just equal f, okay, which is a function of x. Okay. So if we rewrite everything here, and essentially what I'm saying is this: we're going to let all of this be f, and we're going to let all of this be f prime. Okay. So if we rewrite it that way, then this is what our equation ends up looking like. Okay. And if I divide both sides by this constant a here, and I'm just assuming that it's a constant here, then I end up with this expression here. And this is technically a first order linear ODE. Now, it's not in the form that you're used to seeing, but it's there. Okay. If I wanted to put this in a form that you're used to seeing, it would look something like this. And I would essentially have to subtract both of these terms to both sides here. So I would have something that looks like this if it was actually in true canonical linear form. Okay, it would have to look like that. And so if that's the case, then this would actually be your P, and all of this would actually be your R, so that the resulting equation looks like f prime plus pf equals R. Okay. Now, we don't need to rewrite it like this, but I'm just letting you know that whatever you have here, it is actually a first order linear ODE. And by definition, a first order linear ODE, the highest derivative we can have on any function is the first. And we see that. And that's the important part. Okay. So now that we have this, we know that we actually have a way to solve this, or so we think. Okay. But now we keep count of everything that we've kind of dealt with here. So we know that a and b are constants. We have f prime, we got u prime, v prime, y1 prime, y2 prime. And of course, we got corresponding y1 and y2 that's known that goes along with that. And we have u and v that goes along with these that are not known. Okay. And so at this point in our derivation, please realize that we have introduced 6 unknowns. Okay. And of course, you can kind of see them up here. 1, 2, 3, 4, 5, 6. I've listed them down here to be very clear. So we have 6 unknowns, but only 5 equations of significance here. And of course, these are the 5 equations that I'm talking about. So here, of course, to find out U and V, we have equation 4 star above, which is this one, the one that ends up being a first order linear. We have the fact that we let the U prime y1 plus V prime y2 equal F. And of course, F itself is just going to be the antiderivative of F prime. So we have these 5 equations, 6 unknowns. Since we have more unknowns than equations, then by definition, this is a system of linear equations that is dependent, which means that we have a free variable, okay? Or more proper terms, a free parameter, okay? Because if your unknown is something that you allow to just be anything, then the nature of your problem is going to change based upon what you vary it to be. And so thus, we could choose any of these unknown functions to be a parameter, and how we vary that parameter is going to dictate what kind of solution that we get. And so, in short, this is why we call this process here, this method, variation of parameters. Because once you set what the parameter is going to be, then that's going to give you one of the many solutions that you can get from this linearly independent system of equations here. Okay. So therefore, this system of equations technically has an infinite number of solutions. We can allow any one of our 6 unknowns to be a free parameter by allowing it to equal any real number or function we want. Now, it turns out that the easiest and most convenient unknown to select for our free parameter should be F. Okay. Now, the reason for that, because it's the primary function of equation 4 star, and these equations, that equation possesses the most unknowns in it. So simply put, here for our first order linear, if I can tell you what F is, I can solve this equation. Okay. So that's a more simple way to put it. But if I can tell you what F is, and I give you something that will make this equation easy, then I can solve it. And again, it could be anything. I can let this be a function. I can let F be a function. I can let F be a constant. Once I know what the function is, I can tell you what this first derivative is, and I could, solve. So if we let F equal to some real number Z here, then, or real function Z here, then we know that depending upon what we vary F to be, we can find a specific solution for U prime and V prime, and thus find U and V within the family of infinitely many solutions for our system. Okay. So this is the actual system that we're working with here. And once we say what F is going to be, then we're going to see this system of equations here collapse into the 2 systems. The equation, let's try to say that again, is going to collapse into the system of equations with 2 equations, 2 unknowns that you're used to seeing. Okay. I think I got that out right. All right. So since we only need 1 set of solutions and not infinitely many, we will make the selection of F that we'll presume will be the easiest to work with. And in short, if we let F equal 0, that makes life very simple for us. Okay. And before I start reading down here, I'll just kind of make my point by going back to the previous page. So here, if I was to let F equal 0, then it means F prime is 0 as well as F is 0. So all I have left is this equation here. Okay. And so since I already know what y1 and y2 are, I also know what y1 prime and y2 prime is. I already know what G divided by A is. So the only thing that I don't know is what U prime and V prime are. Okay. Now, of course, here that takes care of this equation. If I let this equal 0, then of course I have this equation and I got this one. And I already know what this is because I've set what it's going to be. So this one is no longer needed. And of course I can find out U and V after I find out what U prime and V prime are. So from here, I only need 2 equations to find out what my U prime and V prime are going to be. And that's what you're used to seeing whenever you do variation of parameters. So once you let this equal 0 here, then of course everything is going to simplify to those 2 equations that I talked about, and I'll write it formally on the next page here. And so when I say thus it is convenient for f to equal 0, you kind of see what I mean now. But this double underlined phrase is a phrase that you'll normally see in most textbooks, but rarely, if ever, you'll get an explanation as to why they say it's so convenient to let basically f equal to 0 and to also have this expression equal to 0. But see, now you know why. Okay? It's because f is to be chosen as a parameter in the system of equations of 6 unknowns and only 5 equations. And also the ability to let f be various real numbers or functions is why this method is called variation of parameters. Okay. Now, before we move on, I know I have f is equal to 0 here, but I could have very well said let f be 1, or I could have said let f be x squared. Okay. If I would have done that, I'm going to get different solutions for u and f. Okay. But whatever I get, it will still end up working, meaning that based upon what I let f be, the corresponding result for u and f, it's still going to end up being a solution for my non-homogeneous equation that I started to work with. And so because of that, that's showing you that this uy1 plus vy2, the fact that these functions here can be an infinite number of combinations based upon what I let f be, is sort of acting like the constants for a homogeneous solution. Well, we said for a homogeneous solution, we have c1y1 plus c2y2. So we know that based upon what c1 and c2 could be, and they're arbitrary, we could find out other solutions for the homogeneous equation. Well, the fact that we have infinitely many solutions to this, each combination of u and v, even though their functions are sort of acting like the constants do here. And so that is what we meant when we said, well, hey, let's assume that our y sub p could be solutions of this form. We wanted to act like this did. And now we see that it has a potential to be able to do that. But again, to make life simple for ourselves, the easiest thing that we can allow f to be is 0. Okay. And just so that you know, if you allow f to be anything else, you have to go through more work to get to your solutions for u and v, but you can get to it. Okay. All right. So now that we do all that, we let f be 0, which means f prime is equal to 0. We see that the result ends up being this equation here. Once we excuse me, once we actually simplify everything, and thus here's our system of equations here where we let f equal 0. So that means this is going to be equal to 0 as well. And what this is going to boil down to is we're going to have these 2 equations here. Okay. And so this is what you see when you talk about variation of parameters by doing it the traditional way. Okay? All right, so now we're going to state variation of parameters, derive the formula way. So once we have this system of equations here, if we actually use the substitution method, you'll actually see how we back our way into the formula for solving a second order linear non-homogeneous ODE by using the formula way, okay? So using substitution method, I just rewrite this first equation to equal y prime. And of course, this lets me know, sorry, not y prime, u prime. And I take the antiderivative of that answer to figure out what u is. Take that result for u prime, and I can actually stick it in here to figure out what my v prime is going to be. Okay, so as you can see, I've done that here. Do my steps and find out what v prime is going to be. And so v prime ends up being this result here. And if you remember from the part 2 video and part 1 video, that this g divided by a times y1, this was just the Wronskian matrix for when k is equal to 2. So in other words, Wronskian here, but you replace the y2 prime with 0 divided by g minus g divided by a. And of course, if we do the same thing here for u prime, you're going to see that that tends to work out to be this Wronskian sub 1 divided by the Wronskian. Okay. So once we work out everything here, we see, once we know exactly what this is going to look like, we can substitute that back into u prime, and we see this ends up looking this way. And of course, from that, if we go and just basically substitute everything in for the y of p, then we're going to have y1 times all of this is going to be your u, and then y2, all of this is going to be your v. And then of course here, all I'm saying is that if I was to actually explicitly write out the integration constants as well, I could recover my homogeneous solutions here, okay? But I don't have to, because I already know what my homogeneous solution will look like. So it's just going to be this plus what this ends up being. And of course, that ends up letting me know what my formula is going to look like whenever I'm dealing with the second order linear ODE. Now, finally, if we do the same thing for, let's say, a third order, then much of this process is going to be the same. The only thing that's different now is, of course, there's more work to do, but your result ends up being a system of equations where you have 3 equations, 3 unknowns, instead of 2 equations, 2 unknowns. And then, of course, from here, the formula for how we get to our total solution y sub x, or y of x, is going to be the same. Our Wronskian for this case will be the Wronskian of the basis of our third order linear ODE, which would be y1, y2, y3, and all its derivatives up to n minus 1. In this case, n will be 3, so we'll have a row with the original function, a row of the first derivatives, a row of the second derivatives. And again, let's say Wronskian 2 would just be the same as this, but we replace this particular row with all zeros except for the last entry is g divided by a. Okay. And of course, for our nth order, if we were to extend that on out, we'll see that it ends up equaling this formula here. And of course, this was the formula that was quoted in the part 1 video. But now you see how we actually get to that. It's just literally doing reduction of order, figuring out, hey, at the end of the day, we need to have this first order linear ODE. From there, we engineer the equation to where we find an expression to name a function of x, and we just let that equal 0, and then everything seems to work out fine. All right, so hopefully this video helps you to be able to understand how and why variation of parameters actually works, and why we call it what we call it. And hopefully this will also help you to be able to retain this particular process whenever you're working on problems in the future. Take care.